Welcome to 66th lecture. We are studying circuit analysis and we'll continue power factor in a three-phase load. In our last lectures, we have been studying about three-phase load, both delta and Y connected and their various characteristics. In this lecture, we'll study about the power factor of our three-phase load. Right. In a delta connected load, we know we have the voltage in each phase. Across each phase, we have the line voltage across the Z delta, the per phase impedance, whereas we have the phase current IAB or IBC or ICA flowing through the unit load or flowing through the load in a phase. So the power factor of a phase is the cosecant of angle between the voltage across the per phase impedance minus the angle of the current flowing through it, right? So if we have same Z delta in each phase, we have the same power factor in each phase, which is actually the power factor of the delta connected load. Similarly, for a Y connected load, for each phase we have phase voltage VAN, VBN or VCN across it, and the current flowing through it is IA, IB or IC, the line current. So we have power factor of load for a Y connected system is the cosecant of angle between this phase voltage minus the angle of this line current. So since Cy remains the same for each phase, all the three phases, so the power factor remains the same, which is actually the power factor of a three-phase load. For both delta and Y, all three phases contain the same Z delta or Cy. Therefore, the power factor remains the same for each phase, right? Which is actually the power factor of the load. To better understand the concept of power factor in a three-phase load, we'll solve this example. This is a very illustrative example in which a delta connected load, this one, is driving three delta connected loads. The three delta connected loads have different impedances, Z delta 1, Z delta 2, Z delta 3 per phase, and there are some other information given about these loads. P of the first load is 24 kilowatt, the average power. The power factor is 0.6 lagging for this load number 1. For load number 2, we have average power given to be 10 kilowatt and its power factor is 1. This means there is no inductor or capacitor, it's only resistive. And for the third load, we are given the complex power, not the active power, it's complex power. So we are given the complex power and its power factor is leading. This means it contains a capacitive load instead of inductive load. This is a capacitive load, a resistor and a capacitor in each phase. So we have a capacitive load here. We are also given that the line voltage, the magnitude of line voltage is 208 volts. We have to find the magnitude of I, load, the load current, and we have to find out the power factor of the load. When we say power factor of the load, this means we have to find the collective power factor of all these three loads. And when we say we want to find out IL, this means we have to find IL for considering that all these parallel connected loads, they form one load, a single load. The collective IL, the total IL that is supplied by the source, right? So before we compute our unknown quantities IL and the power factor, let's first compute S1, S2 and S3. S3 is already given. Let's compute all these. S means the complex power for this load, for this load and for this load, right? We know that for load number 1 we are given power P1 is 24 kilowatt. So to find S1, we know it's an inductive load, so therefore the power triangle is like this. Q is positive. For a capacitive load or for a load where we have a leading power factor, Q is negative and it is downwards. We know that. P1 is 24 kilowatts. So theta is also given. Oh, it can be computed. It's given that the load has a 0.6 power factor lagging. So theta would be cosecant inverse of 0.6 comes out to be 53 degrees. So this theta 1 is 53 degrees. We know that this theta is we have already studied that this theta is the inverse cosecant of the power factor. So Q1 can be computed as we know that's a right angle triangle. Perpendicular over base Q1 over P1 is tangent of theta 1. So we can compute Q1, which is 32 kVAr, kilovar, and then S1 can be written as P1 plus JQ1. We already know that S is the complex power. It's the average power plus J times the reactive power. Similarly, for S2, it is given that the power factor is 1. When power factor is 1, this means Q2 is 0. There is no inductor or capacitor in the load. So the S is the same as P. Finally, let's compute S3. It is given that it has a 0.8 leading power factor. Leading power factor means a negative Q. Leading power factor means a negative Q. So theta 3 is inverse cosecant of 0.8, 36.9. S, the magnitude of S is given, it's 12 kVA, and at an angle of minus 36.9. We know that this is the angle S. Theta 3 is the inverse, cosecant inverse of the power factor. So we can convert this number into rectangular form and it comes out to be this much. Finally, we know that S load would be the sum of the S of the three individual loads connected in parallel. So we have also written S1, S2 and S3 in terms of their rectangular representation. So that's easier to add because we can add real part in real and imaginary in imaginary. Or we can convert this number to polar form. It comes out to be this much. There is a small recap because before we find the first unknown IL, there is a very small recap from the last lectures. So now we are ready to find the first unknown IL, but before we compute that, let's go through this small recap. The small recap is this much. About the magnitude of S. We know that S is a complex number, which is P plus minus JQ. And we can also write P as square root of 3 VLIL cosecant of theta. We studied that this is the three-phase power, the active three-phase average power. This is the expression for three-phase reactive power. When we find the magnitude of S, this is the magnitude of S. This means this would be the real squared plus the imaginary squared and the whole square root, right? So when we do that, this square root of 3 VLIL is common squared, and then computing square root, it comes out of the square root, and cosecant squared theta plus sine squared theta. We know it's a trigonometric identity. Cosecant squared theta plus sine squared theta is a 1. Square root of 1 is a 1. So the magnitude of S is our square root of 3 VL times IL. This is a very useful expression that we'll use here. We have just computed S load. S load, we know VL, it's 208 volts. It's given in the question, and then there is only one unknown in this expression, IL, which we can compute. Right. So to compute IL, we had to go through a small recap. And the second unknown in this question is the power factor of the load. Let's draw a power triangle for the complete load. This is the power triangle. Before this, we have been drawing power triangles for individual loads. Here is the power triangle for the joint load. P of the load, Q of the load, and this is S of the load, the hypotenuse. And we know that theta this is not old, this is load, LOAD. The small mistake, it's not old, it's load. So theta of load is 29.63 because we already know that S, we have just computed, is 50,160 at an angle of 29.6. So this is the same angle as the angle of this power triangle. And what should be the power factor of the load? That is simply, we have already studied that cosecant of this angle is the power factor. So cosecant of the angle is 29.63, 0.89 lagging. This means a positive P and a positive Q. Right, that's all for this lecture. We'll continue studying more about power factor in three-phase circuits in our upcoming lectures. Thank you.